Welcome to our second portion of 3.9 related rates. We're going to be looking at some questions that sometimes cause people to have a little bit more difficulty. And so, my biggest hint here would be draw yourself a picture, label what you can label, identify what you know and what you're being asked to find. Usually, in these problems, they don't flat out tell you all of your missing pieces. So, what I mean by that is they're going to give you a set of information and they're going to ask you to find something. Usually, there's other information you need to know as well in order to find what you're being asked to find. They do give you enough information to find those missing pieces that you need, but they most of the time will not just straight out say, here's what you need, go. That would be too easy. So, my biggest suggestion would be draw yourself a picture, label it, and that will help you identify what else you can find and what you're being asked to find in the question. Okay. So just a reminder, your related rates, we're talking about how fast does something change as something else is changing. So we looked at things like a cylinder. If you change the radius of a cylinder, the volume would change. You make the radius smaller, the volume would be smaller. Make the radius bigger, the volume would be bigger. And how fast you change the radius helps determine how fast the volume would change. It's not a one to one correspondence, but there is a relationship between the two based on what the relationship between volume and radius is. So today we're going to be looking at two main types of questions, and you will see these quite a bit. One is a ladder leaning against a wall, and if the ladder's falling down the wall, what can we determine? The other one is baseball questions. If you have somebody running around a baseball diamond, most of the time we're looking at the distance between the runner or the baseball player and home plate. There is one other type of question that you will see commonly, which is if you have cars heading towards an intersection or away from an intersection, how fast is the distance between those cars changing? So there are a couple of those questions in your various practice materials that I've given you. If you're having trouble with those, of course, there's tons of examples online and on YouTube. If you search calculus related rates, cars moving, I'm sure you'll find lots of examples on YouTube or Khan Academy, etc. But draw yourself a picture, label your diagram. Most of these are dealing with triangles, so you'll need Pythagorean theorem for these questions. Okay. So our first question says, after a fun morning in the snow, Emily props her 1.5-meter aluminum sled, that's going to be an important piece of information, up against the house and goes for lunch. The sled slides down the wall of the house and makes a loud noise, which scares the neighbor's cat. When the bottom of the sled is 1 meter away from the wall, it's slipping farther away from the wall at 15 centimeters per second. And it's asking how fast is the top of the sled moving down the wall. So I'm going to draw myself a picture. Here's my house. I guess it's snow, so grass isn't probably a good idea, but here's my grass. Okay. And here's my sled. So my sled is 1.5 meters long. Okay. And it's telling me that the bottom of the sled is 1 meter from the wall. Okay. Now it's also telling us that the sled is slipping farther away from the wall. So the bottom of the sled is moving away from the wall that direction at 15 centimeters per second. And it wants to know how fast is the top of the sled moving down the wall. If we think about this logically, this makes sense. If the bottom slides away from the wall, unless the sled is going to grow in length, the top must slide down the wall, right? So we know a couple pieces of information here. We know the length of the sled is 1.5 meters. Okay. I'm going to call the other sides X and Y. I'm going to call the bottom distance X and the vertical distance Y. Okay. So we know that X is 1 meter and dx dt is 15 centimeters per second. We don't know y and we don't know dy dt. And this is what we're being asked to find. We want to know how fast is the sled sliding down the wall. That would be a rate. That would be, because we called that side y, that would be the change in y over time. How fast is this happening? Okay. So first, I know that I've got a triangle here, so I can use Pythagorean theorem to find y. I also know if I set up that equation, I would be able to find a dx dt and a dy dt. Now we've got a bit of a problem here, like we had last day. We've got 1.5 meters and 1 meter, but my dx dt is in centimeters per second. So I can either choose to change the meters to centimeters or the centimeters to meters. Either way is fine. Just for ease, if you only want to change one thing, change your dx dt, but it doesn't matter. What will change in your answer is your units. So if I change everything to meters, my units for dy dt will be meters per second. If I change everything to centimeters, my units for dy dt will be centimeters per second. So on the PDF copy of the notes on the team, I've got everything in meters per second. So I'm going to do the opposite here. I'm going to change my L to centimeters, and I'm going to change my X to centimeters. And so my units will be in centimeters per second. So if you want to see the other way, if I change everything to meters, you can check the PDF copy of the notes online. Okay. Now I know that I have a relationship between these three sides of my triangle. I know that x squared plus y squared is equal to L squared. So I don't know why. I'm going to need it because if I do my derivative of this, I'd be doing implicit differentiation. I would have 2x dx dt, and I know both x and dx dt, plus 2y dy dt equals 2l dl dt. So I know this, I know this, I don't know this, and I don't know this. I know L, and so my question for you, logically speaking, what would dl dt be? What rate is the length of the sled changing? Well, it's not. The length of the sled is staying the same. So, like we said, if the bottom of the sled moves away from the wall, two things are happening. Either the top of the sled is also sliding down, or my sled is growing, which makes no sense. So, dl dt is equal to 0. So, the problem is we've been asked to find dy dt. We can't do that unless we know y, but we can find y. Have Pythagorean theorem. So to find y, we have x squared plus y squared equals L squared. X we said was 100. Y is what we're trying to find. L is 150. So y squared is going to be, if I grab my calculator here, 150 squared minus 100 squared gives me 12,500. Now I can't square root that nicely, but I can divide this by, I can divide this by 100, which would give me 10 root 125. And I can divide that by 25, which gives me 50 root 5. All right, so now we have 2x dx dt plus 2y dy dt equals 0 because dl dt was 0. We have x is 100. We have dx dt is 15 centimeters per second. We have 2y is 50 root 5. We just double check that's accurate. Yep, we're good. Okay. And dy dt we don't know. And we can solve for dy dt. So I'm going to actually multiply my 2 and my 100 and my 15. I get 3,000 plus 100 root 5 dy dt. And then I can move the 3,000 over. I can divide by 100. Okay. And then I can divide by root 5. Now, because we changed everything into centimeters, this is going to be centimeters per second. You can leave it like this if you'd like, or you can rationalize and have this be negative 30 root 5 over 5, which would be negative 6 root 5 centimeters per second. So both of these are fine. Most of the questions will ask you for an exact value you would want to leave like this. If you've been asked to say round it to the nearest decimal place. So if you want to evaluate exactly, leave root in your answer. Otherwise, we'd have dy dt equals negative 13.42 centimeters per second. So if we did this in meters per second, we would need to divide by 100, which is the answer that we have in the PDF copy that has been uploaded. Now, also, the fact that this is negative should make sense because we're sliding down the wall. If we were sliding up the wall, we would have a positive rate. But because we're sliding down the wall, we get a negative answer. So the second type of question we're going to do today is a baseball question. These are common. Just make sure you are reading the question carefully so that you can label your diagram. So for example, sometimes they'll try and throw you off and they'll say, well, you're running from second to third, but it will give you your distance from second instead of your distance from third base. So if you're not familiar with baseball, there are 3 diamonds and a home plate. Okay, so if I draw my picture, I'm going to draw it like a square just for ease of my diagram. Okay. So usually we have a home plate, and then going around counterclockwise, we have first, second, and third. Okay. And effectively, when you're on the field, you would stand at home and look out, and it would look like a diamond, but the corners would all be right angles. So it says it's a square whose sides are 90 feet long. And so suppose Derek Jeter is running from second base to third base. So he's running this direction here. Okay. And he has a speed of 30 feet per second. And it's saying at the instant when he is 20 feet from third base, so when he's about here, and this is 20 feet, okay, what rate is his distance from home plate changing at that instant? So if I draw a line from Derek Jeter standing here, 20 feet from third, to home plate, you can see that we have a right triangle here. So I'm going to call this H for distance from home plate. We know that this other side of the triangle is 20, and we know the third side of the triangle because the question tells us the square has sides that are 90 feet long. So we know this is 90 feet. So we know that we have 20 squared plus 90 squared equals H squared. So we can find the actual, at that instant, how far away is he from home plate? But since he's running towards third base, right, we know he's running this direction. The closer he gets to third, the distance from home plate will change. Okay. So, what we need to find out is we've been asked what is the rate that that is changing at. We're asked for dH/dt. We've been given the distance between Derek Jeter and third, and we've been given the rate at which he's running. Okay. So again, I'm going to call these different sides X and Y. So I'm going to call the 20 feet X and the 90 feet Y. So we've got X squared plus Y squared equals H squared. And if we do the derivatives here, we get 2x dx dt plus 2y dy dt equals 2h dh dt. So we've been asked to find h dt. We have the information to find h. We know x and dx dt. dx dt was 30 feet per second. X was 20. We know y is 90. So the only other thing in the question is what is dy dt? We need that in order to find dh dt. So again, if I think about if I'm running towards third, the distance between me and third is changing, and the distance between me and home plate is changing. What is the rate at which the distance between home plate and third is changing? So dy dt is asking us how fast is this side changing? Well, it's not. Third plate and home plate are not moving. They're stationary. They are 90 feet apart. There is no rate of change. They are not moving. So this is equal to 0. And this will often happen, not on the car questions so much, but usually one of these is a speed of one car and one is a speed of another. But in this question, the previous question, we have some fixed value that is not changing, making the rate of change of that side of the triangle 0. So for us, third and home plate are not getting any closer together or any farther apart. The rate of change of the distance between those two is 0 because the distance between third and home is not changing. Okay? The distance between me and third, or Derek Jeter and third, is changing. I'm running towards third, and the distance between me and home, or Derek Jeter and home, is changing as I run along that line from second to third. So if I'm standing over here, you can see that my distance from home plate is different. Okay, so where I am in my run matters. Okay, so now that we have all this information, we're going to find h, and then we can find dh dt. So we've got 20 squared plus 90 squared. So we've got 8,500 is h squared, or 10 root 85 is h. If I simplify that, I can divide 8,500 by 100, and I can take that out of the radical. Okay. Now, once I have that, I have 2x dx dt plus 2y dy dt equals 2h dh dt. And now 2x, x was 20, dx dt was 30 feet per second. dy dt is 0, so this entire second term becomes 0. 2h is 2 times 10 root 85, and we don't know dh dt. So we're going to fix this up a little bit. We've got 2 times 20 times 30. This gives us 1,200 equals 20 root 85 dh dt. So if I divide both sides, we should be able to fix this up at least a little bit and get 60 over root 85. And again, if we look at the units in the question, it's a distance in feet, and he's running in feet per second, so the distance changing would be feet per second. Again, you can leave your answer like this if you'd like. This would be an exact answer. Okay. You could also rationalize. So if I rationalize this, I get 60 root 85 over 85. And then I would need to simplify. I need to divide these things by 5 and get 12 root 85 over 17 feet per second. Okay. This would be another exact answer. And if I wanted to evaluate it, I would get 6.5 feet per second. So in your folder for this day, there is a practice worksheet you can try. And the answers are on the bottom of the page. So you can try those practice questions, and hopefully you will be able to get through those. So that is all for today.